Divisibility in Modular Arithmetic, Section 4.1. Okay, so we're going to, just like how we defined odd and even numbers, we're going to go back and redefine division. Now, in this case, we're just defining what it means to be divisible. So if we have an a and b that are integers, with a cannot be 0, we say that a will divide b, and we denote it a vertical bar b. So don't think of this as actually doing the division. This is a statement about whether or not it is divisible, right? The result of this will be a true false. If there exists a c such that a times c is b. So it's kind of like asking, is a factor? Now, this is the same as stating that if you take b and you actually do divide by a, the result should be an integer. If a divides b, then a is a factor or divisor of b, so b would be a multiple of a. I find it really helpful to think about that second part, a is a factor of b, when I see this definition. So we're going to go through, we're going to apply this a couple times. Don't get too caught up on actually doing the division. We put that same bar with a slash through it when a does not divide b. So for example, if we wanted to determine, does 5 divide 17? Well, here we can apply it pretty quickly. We can say, well, 17 divided by 5, that's not an integer, so 5 does not divide 17. Does 5 divide 20? Well, 20 can be written as 5 times 4. So 5 does divide 20. So note there, I didn't do the division and then tell you the answer. It's going to be important coming up. We want to, as much as possible, focus on applying the definition here as a factor rather than actually doing the division. Does 9 divide 48? Here, 48 divided by 9 is not an integer, so 9 does not divide 48. So we get a couple statements. We have a theorem, if a, b, and c are all integers, a is not 0. If a divides b and a divides c, then a will divide the summation. You can almost visualize this right now, right? You factor the a out of b, you factor the a out of c, then you can factor the a, right, out of the grouping b plus c. If a will divide b, well then naturally it will divide b times any c, because it's already a factor of just b. And if a divides b and then b will divide c, then a will divide c. That's an application of that definition. Again, at least for me personally, when I think of it as factors, it makes a lot of sense. So let's prove 3 though, just so we can see how a proof applying this divisibility definition might work. So note that I'm not going to do the division, I'm going to apply the definition of divisibility. So if I want to show that 3 is true, I'm going to do a direct proof. I'm going to assume a divides b and b divides c. What does that mean? Well, by definition, that means there exist 2 integers such that b can be written as a multiple of a and c can be written as a multiple of b. Well, now we combine these 2 facts, right? Taking that second one there, c equal bk2, and we can rewrite typo here. Give me just a moment. Here we go. Okay. So grabbing that second one, I can replace the b with a k sub 1 and then factor the a out of there. So I now have a times k1, k2, but k1 times k2 is of course just an integer. So I've shown that a times an integer gives me c, therefore a divides c. Get a quick corollary from this. If we let a, b, and c all be integers where a is not 0, a divides b and b divides c, then a will divide any linear combination of b and c. That is, we can multiply b times an m and c times an n, any integers we want for b, m, and n there, and then add them up and a will still divide it. This comes directly from 2 of the statements in the theorem. So one of the major focuses in this chapter is going to be the division algorithm. If we let a be an integer and b is a positive integer, then there exists a unique q and r in the integers where r is between 0 and d, such that a is equal to d times q plus r. D is the divisor, A is the dividend, Q is the quotient, and R is the remainder. So what we state is Q is equal to A divide by D, and R is equal to A mod D, right? The remainder and the quotient. So what are the quotient and remainder when 44 is divided by 8? We write it in exactly this form, this A equal DQ plus R form. We can write this in this case as 44 is equal to 8 times 5 plus 4. So 44 is the dividend, 8 is the divisor, 5 is the quotient, 4 is the remainder. So we would state that 44 divided by 8 is 5, and 44 mod 8 is 4. What about when we take the negative 37 divide by 6? Now this one is really tricky. We end up writing it as negative 37 equals 6 times negative 7 plus 5. And that may not be what you would get if you sat down to write it on your own. The thing to remember is that from the definition here, from the algorithm, R has to be positive. So we actually end up with more copies of 6 than you may expect to sort of pass up negative 37 and then come back with a positive remainder. So negative 37 divided by 6 is negative 7, whereas negative 37 mod 6 is 5. Again, the common answer, the one I want to really spell out here that we want to avoid, is that you may be thinking, oh, well, this is just 6 times negative 6 is negative 36. Give me a negative 1, that'll get me there. But the R has to be positive. So it is not, the division algorithm does not give us negative 37 written as 6 times negative 6 plus a negative 1. What about 58 divided by 7? Pause it, give this one a shot real quick. We can write 58 as 7 times 8 plus 2. So 58 divided 7 is 8. 58 mod 7 is 2. Now, one common place you run into this idea of modular arithmetic is with a clock. So say I ask you, what time does a 12-hour clock read 30 hours after 7? Well, to do this, you're really thinking, okay, well, 30 hours after 7 means a total of 37 hours have passed, and you're just going to start rotating that hand around the clock. So 37 mod 12, well, how many times does 12 go into 37? It will do it 3 complete times, 3 complete rotations of the clock, leaving 1 hour left. It will be pointing at 1 o'clock. So just a quick warning here, depending on the programming language you're using, make sure you check the modulo function. Some of them use the ceiling. We want the floor version of this. So just make sure that whatever language you're using gets the same answers that I've been displaying so far. So what's the advantage? What's with all this modulo stuff? If a and b are integers and m is a positive integer, then we say a is congruent to b modulo m if m would divide the difference between a and b. In this case, we have a is equivalent to b mod m. So we would say that a is equivalent to b mod m is a congruence and m is its modulus. So we would then also be able to say that a is not congruent to b mod m when a is not congruent to b. We're going to go through several ways to approach this, to think about it. You pick the one that clicks the most for you. So determine if 17 is congruent to 31 modulo 7. So we're living in a modulo 7 world. So the question is, will M divide the difference between A and B? In this case, that's asking, does M divide the difference between 17 and 31? Are they off by one rotation of the clock? The result is a negative 14, which 7 certainly does divide. So since it does do the division, we can say that 17 is congruent to 31 mod 7. What about 25? Is 25 congruent to 6 modulo 7? Again, we apply the definition here. Will 7 divide the difference between the two? In this case, does 7 divide 19? No, it does not. So we would say 25 is not congruent to 6 modulo 7. Another way to think about a congruence relation is that we can easily reverse the two, right? That's why we kind of have modulo M in parentheses there. I'm not saying take the mod. I'm saying in a modulus M world, right, where all the numbers have been modded by M, right? Is it a 12-hour clock? Is it a 13-hour clock? What are you asking for here? So we can say that A is congruent to B mod M, and that is if and only if B is congruent to A mod M, right? The order there doesn't really matter. We can prove this going in one direction relatively quickly. If we assume A is congruent to B mod M, that means M will divide the difference. That means there exists a K, right? By the definition of does divide, there exists a K where the difference is a multiple of M. But then if we just multiply both sides of that statement by a negative, we get B minus A. Well, now M also divides that with factor negative K. Therefore, M will also divide B minus A. Going the other way is very, very similar. So this happens to be the way that for some reason I like to envision these. But if A is congruent to B mod M, it's saying there exists an integer where A is equal to B plus Km. Right, that A and B are both pointing at 1 o'clock, just one of them has gone around the clock more times than the other. Determine if 17 is congruent to 31 modulo 7. We've already seen this before, but now let's try and apply this new if and only if statement from this theorem. Sure enough, 17 can be written as 31, that's our B, plus negative 2, that's the K, times 7. Right, it's to get to 17, you point the clock at 31 or whatever result the 31 hours will point at, and you rotate it back 2 full rotations. Congruently, that means you could also point at whatever 17 hours would point to. Right, you start at 0, rotate the clock 17 hours, and if you do two full rotations, you'll get to whatever 31 hours would point to. Next, we have that A, B, C, and D are all integers. Again, M, our modulo, is always going to be a positive integer. If A is congruent to B, C is congruent to D, then that would imply that A plus C is congruent to B plus D, and A times C would be congruent to B times D. A real quick example of this, let's look at 25. That's congruent to 0 in a mod 5 world. 42 is congruent to 2 mod 5. So if we add these two together, 25 plus 42, that's congruent to 0 plus 2 in a mod 5. Looking at the second line, that's not as clear, but on the second line there, it should become clear because we can do divide by 5 really easy in our head. When we take 67 and we divide it by 5, well, your multiples of 5 always end in a 0 or a 5. So we can obviously a multiple of 5 is would get us to 65. That leaves a remainder of 2, meaning that 67 mod 5 is 2, and 2 mod 5 is 2. Looking at the multiplication there, if 25 already has a remainder of 0 when we divide, then 25 times 42 would provide us with a 0 as well, a 0 remainder when we division by 5. And finally, this theorem is one we're going to use a lot in the next chapter. So here we're not talking about congruences, those are equal signs. So we're actually going to take the mod. We want to know what the remainder actually is. If you add a and b first and then do mod m, that's equal to taking a and modding by m, finding that remainder, then doing b, modding by m, finding that remainder, and adding them together. But the trick is, after you do that, you need to mod again. You know, if our remainders are both really close to m, then the sum would be above m. So we need to take that mod again to bring it back in line. The same thing for multiplications. So for example, if we take negative 133 mod 31, and we're going to add to that 270 mod 31, then the result of that we would still need to take mod 31. In this case, we get 13. Now compare that to the other side, the a plus b mod m. So here I'm going to add negative 33 and 270 first. And then I'm going to mod m, I'm sorry. Slight typo here. So now I'll take negative 131 and add 270 first, then I'll do the mod m. Now the trick here is that in green, the left side of this equality, I only had to do one modulo and I only had to do one addition. Compare that to the part in blue. I had to do 3 different modulo calculations and 1 add. So in terms of time complexity here, we can see that using this equality and doing the green might save us some steps, but it is important to note that we can do either of these. They're equal.